Then write moment equation for last segment AB. So for this segment, I consider A as origin and limit will be 0 to 4. So distance between A to B is 4 meter. Our reference is x, origin is A, so therefore x is equal to 0 at A and x is equal to 4 at B. Okay, so now I consider section XX is x distance from the point A. Then write the moment equation on the left of the section XX. So on the left side, so only 3 forces. On the right side means we have to consider VD, HD, then 20 kilonewton, then 10 kilonewton, totally 4 forces. On the left side means it is more convenient compared with the right side, so that's why I chosen left side of the section. So on the left side, so only 3 forces, so one less HA force. So HA force, it creates sagging moment about section XX. So therefore moment will be HA into X. Then VA force, it is a vertical force, its line of action lie at the section XX. So for this VA force, there is no perpendicular distance, therefore it can't produce any moment. Then one more moment is there, so moment is MA. Okay, it creates a hogging moment, so therefore the equation will be HA into X minus MA. So let's simple. Okay, then substitute MA. So we already determined the MA reaction. Support MA moment 100 minus 6 VD. HA is equal to 10 minus HT. Okay, this thing we already determined. Okay, HA is equal to 10 minus HT, VA is equal to 20 minus VD, MA is equal to 100 minus 6 VD. So substitute these things. The final equation will be minus 100 plus 6 VD plus 10x minus HT into x. Then differentiate this moment equation with respect to partial differentiate with respect to VD. Okay, so that gives 6. Then partial differentiate with respect to HD means it gives minus x. Then substitute the above expression mx dou mx by dou VD dou mx by dou HD in the above equation for equation 1 and 2. So equation 1 becomes, okay, what is the equation 1? So equation 1 from the theorem of least work, so dou u by dou VD is equal to integration of mx dou mx by dou VD into dx divided by a equal to 0. Second equation, dou u by dou HD is equal to integration mx dou mx by dou HD into dx divided by a equal to 0. So substitute these mx dou mx by dou VD dou mx by dou HD in the above equation. So finally the first equation becomes dou u by dou VD is equal to integration of first segment DC segment, then CE segment, EB segment and ABC segment. We have to consider the entire structure. Okay, so in the entire structure we I split it into 4 segments. So therefore, so add all the 4 segments finally equal to 0. Then substitute these values. For the segment DC, limit will be 0 to 4. Mx is equal to minus HD into x. Mx is equal to minus HD into x. Then dou mx by dou VD is equal to 0 divided by EI. So in the frame EI is constant. Okay, don't need to bother about this EI value. So in the previous problem it is a non-prismatic beam, so therefore we concentrate so where the moment of inertia changes like this. Okay, like all. So in this case, so moment of inertia is constant, so just you may neglect it. Okay, it is not a problem. So then second segment, that is CE segment, so limit will be 0 to 3. So moment equation mx is equal to VD into x minus HT. Then dou mx by dou VD, dou mx by dou VD is equal to x. Okay, then third segment EB segment, limit 3 to 6. So moment equation will be VD into x minus 4HT minus 20 into x minus 3. Then dou mx by dou VD is equal to x. Then fourth segment moment equation, limit will be 0 to 4 minus 100 plus 6 VD plus 10x minus HD. This is mx. Then dou mx by dou VD is equal to 6. so equal to 0. Okay, now expand it and integrate it. In the first term, if the 0 is there, therefore this term is equal to 0. Then second term 0 to 3, then multiply x inside, so therefore v dx square minus 4 dx by I into dx. Then next portion, limit 3 to 6, integration 3 to 6, then expand it, then finally integrate it. The final equation will be 216 Vd minus 120 Hd is equal to 2370. So take this as equation 3. Okay, after substituting the mx and the dou mx by dou Vd, then multiply these two things, then expand it, then integrate it. Then first equation is becomes third equation, so that is 216 Vd minus 120 Hd is equal to 2370. So this is third equation. Then second equation is dou u by dou Hd is equal to, so again the 4 portion, okay, 4 segments DC, CE, EB, then AB is equal to 0. Okay, so then the first segment again limit 0 to 4, so moment equation is equal to minus Hd into x, then dou mx by dou Hd is equal to minus x. Okay, so this term is mx, this is dou mx by dou Hd minus x. Then for CE portion, limit 0 to 3, then moment equation Vd into x minus 4 Hd, then dou mx by dou Hd is equal to minus 4. Like third portion, EB portion, then AB portion. Okay, then finally integrate this equation, then substitute its limit. The final equation becomes minus 120 Vd plus 138.66 Hd equal to minus 946.67. This is equation 4. Okay, so now solving equation 3 and 4 by calculator, or you may use a matrix approach. We get Vd is equal to 13.827, Hd is equal to 5.139. Okay, so this value is in positive. Initially we assumed the direction, so Vd is upward direction, Hd in towards left direction. Okay, if this value is positive, means our assumed direction is correct. So in case sometimes these values may be negative means our assumed direction is wrong. That's it. Okay, so from that determine another support reactions. Ha is equal to 10 minus Hd, then Va is equal to 20 minus Vd, Me is equal to 100 minus 6 Vd. Okay, after substituting these things, we know all the support reactions. Now draw the shear force and bending moment diagram for the frame. So for this, first draw the free body diagram for the segment. Okay, for the column, free body diagram for the column CD. Okay, so this is C, this is D. So at the D, so two reaction, one is Vd, so Vd is equal to 13.827, then Hd is equal to 5.139. Okay, so at the C, so it is a two-dimensional frame. Okay, so at the every point we have to consider, at any section we have to consider three kind of forces. One is axial force, then shear force, then moment. Okay, so therefore, so at this point consider one axial force. Okay, so take some Vc. Okay, axial force, then one shear force Hc, then one moment Mc. Okay, then apply equilibrium equation of this segment. So once again you may apply, so vertical equilibrium equation, summation of V is equal to 0 means Vc is equal to 13 point, Vc is equal to Vd So that is 13.827. So VD is upward direction, VC is in downward direction. Then apply second equilibrium equation, summation of H equal to 0. So from that equation, so HD its action towards left, HC on the is in right direction. By applying equilibrium equation, HC is equal to HD is equal to 5.139. Then so likewise apply third equilibrium equation, summation of moment about point C or point D equal to 0, any point. Then apply it, find out the value of MC. Okay. So after applying the equilibrium equation, we finally found so these values. Okay, I already said. So HD we already known 13.827, HD sorry VD 13.827, HD 5.139. Okay, so then VC also 13.827, HC 5.139. Then moment is equal to, that is MC moment is equal to 20.556. that is in Hawking moment. Okay, like second segment. Second segment, CE segment. Okay. Then next draw the free body diagram for CE segment. Okay, so we already known the value of HC, VC, then MC. Okay, for the joint equilibrium, so for the beam we have to consider the opposite signs. Okay, so in the while considering in the column segment, HC is in right hand side. For the beam segment, it is in left hand side. For equilibrium, net force at the joint will be equal to 0 for joint equilibrium case. Likewise, we see in downward direction. So in this point, we consider it is an upward direction. Then this moment is in the column segment. This moment is in anti-clockwise direction. For the beam segment, it is considered clockwise segment. Okay, then we have to consider at the E point. Okay, so at the E section we have to consider three forces: one axial force, then shear force, then moment. Okay, apply equilibrium equation once again for this segment. Finally we found VC is equal to 6.137, HC is equal to 5.139, then MC is equal ME is equal to VE HE ME is equal to 20.925. Okay, so likewise you may draw the free body diagram for each and every segment and determine the axial force, shear force and bending moment at the each nodal point, each important point. Okay, so like A point, B point, C, D, E points. Okay, after that you may draw the shear force diagram. Okay, so shear force diagram. So for the CD segment, so shear, you already know about how to draw the shear force and bending diagram and the strength of material itself. So in case of structures, the bending diagram, most common bending moment diagram will be a superimposed bending moment diagram. So most of the problem we are dealing the indeterminate structure. So indeterminate structures are subject to both hogging moment and sagging moment combinationally. Okay, so most of the joints are subjected to it's subjected to both hogging moment and sagging moment. So for this we may use the superimposed bending moment diagram like this. So this is superimposed bending moment diagram. So at the joint A, so a hogging moment. So from the free body diagram you may find out the moment at each and every corner. Okay, so at the joint A it is subjected to the hogging moment of 17 point something. Okay, 17.038. At the joint B, so it is subjected to sagging moments. Okay, so at the joint A for hogging moment you may draw a line in this direction. Then at the joint B it's subjected to the sagging moment, so it is considered in downward direction. Okay, then connect these two lines, so it represents the fixed end moment of AB portion. Then again we can draw the shear force bending moment diagram, fixed end moment diagram for BC, beam portion at the B. So again sagging moment, it is represented downward. Okay, so this is 2.406. Then at the joint C, it is subjected to the hogging moment of 20.556. Okay, so it is in upward direction. Then connect these two. Then for CD portion, C joint C is subjected to hogging moment 20.556. Joint is subjected to 0 moment. So this is fixed end moment diagram. Then now superimpose the simply supported end moment diagram. Okay, this is fixed end. Now superimpose the fixed end moment, simply supported moment diagram. So that is for the BC portion. BC portion, it is subjected to only point load at the middle span. So therefore moment, simply supported beam subjected to point load at the middle means maximum sagging moment will be WL by 4. So sagging moment, so it is 0 at the end, maximum at the center, its value is WL by 4. Okay, so this diagram represents the superimposed bending moment diagram. So one more diagram, or you may draw actual net value of bending moment diagram at a bending moment at each and every section, like in strength of materials. At the point A, it is subjected to the net moment, hogging moment of 17.038. Then joint B subjected to the sagging moment of 20.406. Then joint E subjected to the sagging moment of 20.925. Then joint C subjected to the hogging moment of 20.556. Then joint D 0. So this is a net moment diagram. So previous one is superimposed diagram, that is, so we superimpose the fixed end moment with simply supported moment, that is hogging moment. First draw the hogging moments, fixed end moments, that is joint A, B, C and D. So what is the moment at these joints? Then draw the bending moment diagram. Then superimpose the sagging moment. Then final moment diagram will be like this.